Hello and welcome to lesson 6.6, intersections of planes. First we're going to look at how two planes can interact in 3 space. So in 3 space you can have an infinite number of solutions with 2 planes, and they can intersect in the form of a line. You could also have 2 planes that don't actually intersect and are parallel, so no solutions. And in the last case, you can actually have an infinite set of solutions where the 2 planes are actually the same. And therefore give you a plane of intersection. Well, if you take a look at the normals, if you have it in scalar form, the 2 normals in the first 2 cases, in the first case, are not equal. I'm going to use the value k as some real number here. In our second case, however, the normals do turn out to be the same, or scalar multiples of each other. It's just the fact that the d values in the actual expressions do not turn out to be the same scalar multiples of each other. Whereas in our last case, the normals do turn out to be the same, or scalar multiples of each other, as well as the d values. So usually it's very easy to tell based on your equations in scalar form whether you're going to have line of intersection or a plane of intersection or no. So let's see how we look at this and how we do this. So to determine the points of intersection between 2 planes, you must eliminate one variable and use the remaining information to determine how the planes interact. So I suggest you use elimination. So let's see how you do this. So let's suppose we have these 2 planes. Plane 1 being described as 3x plus y minus z equals plus 11 equals 0, and the second plane, 4x minus 2y plus z minus 19 equals 0. Well, as you can see, I could just take these 2 planes and add them together, and I can eliminate my variable z. So I get 7x minus y minus 8 equals 0. So what you get is an expression in terms of x and y. What you can now do is solve for one of those variables. So I'm going to solve for y in this case. And I get this expression right here. So what if we let x equal our variable t? Now you can technically let it equal any linear function that you wish, and therefore you'll get the y equals as 7t minus 8, which is also a parametric form of a line. So now all you have to do is substitute this back into one of your original equations to solve for the other variable you don't know. I'm going to substitute in my second one right here, because I think it might be easier to work out the value of z. So 4 times t minus 2 times 7t minus 8 plus z minus 19 equals 0. So I'm going to continue to solve here. I get negative 10t. My apologies, I'm going to solve for z. So that would be positive 10t on this side, and was minus 3 on that side, so plus 3. So therefore, you get a line of intersection. Of x equals t, y equals 7t minus 8, and z equals 10t plus 3. You can also write this in vector form if you prefer. And again, we could have just told that we're going to get a line of intersection, because you'll notice the normals in these two cases are not the same in any way. So this gives you a line of intersection only. Okay, so moving on. So before we continue on with 3 planes interacting, I've got to discuss the topic coplanar. The term coplanar means that all the items, all the vectors, lie in the same plane. So for instance, if I have a plane like this, and I have vector, I'm going to call it n1, another vector, call it n2, and another vector that's also in the same plane, we'll call it n3. Well, these 3 vectors are all sitting in the same plane, so these are called coplanar. And how you check to see if something's coplanar is you do the triple scalar product right here. Again, remember that you got to do the cross product first, then dot it with the last vector, and if it equals 0, it's coplanar. If it doesn't equal 0, then it's not coplanar. And therefore 2 of the vectors could lie in the same plane, but the third vector doesn't. Okay, so there are various different possible solutions that you can have here, in addition to the ones that you had from previous for the 2 planes. So the possibilities are you can have consistent solutions here. These are 3 possible consistent solutions. The first one has one solution. The second one has an infinite set of solutions in the form of a plane. My apologies, in the form of a line. And the last one has an infinite set of solutions in the form of a plane. Well, to test this, you can actually see that all the normals in the first one are not coplanar. So what you'll notice is n1 cross n2 dotted with n3 will not equal 0. However, in the second set, you will see that the normals do turn out to be coplanar. But in our third solution, you'll actually see that the normals are actually scalar multiples of each other. I'm going to use a new variable called m, where m is a real number as well. So this is one possibility that you have right here. These other 3 are another set of possibilities. These are inconsistent solutions. So as you can see, no solutions here. In our second case, it is also no solutions, because there's actually 2 lines of intersection. And in our third case, this is also no solutions, because this creates 3 lines of intersection. Now, in our first case, you'll notice the normals do turn out to be scalar multiples of each other. So they are collinear. However, the d values do not turn out to be the same scalar multiples of each other. In our second case, only 2 of them turn out to be the same. but the third one not. And in our last case, the normals actually turn out to be coplanar. But they do not turn out to be collinear. So even though we have possibilities where they could be collinear or coplanar, doesn't necessarily mean that they have a set of solutions. The only time where we had it so that it was not coplanar, normals, was one solution, and that was on this previous page. Now, I'd be a bad math teacher if I didn't mention anything here, but in our second instance, this is often referred to as a sheaf of planes for a consistent set of solutions. The other two don't have actual names to them. And in our inconsistent set of solutions, the last one is called a triangular prism, or forms what looks like a triangular prism. Again, the other two don't have actual names to them. Well, to find your line of intersection, just like in this one right here, would be the same way that you would in our first example. The other ones where all the other solutions don't actually equal anything, or don't give you a solution, you'll find values of x, y, and z that don't actually make sense or occur. Okay, so in order to solve this, I suggest that you eliminate one variable from one of the equations. If you want something that will always work, start eliminating one variable from the equations 1 and 2. You eliminate the same variable from another two equations. So in this case, if you want, 1 and 3. Use the newfound information and eliminate another variable if possible, and find out your number of solutions from that result. So let me show you an example of this. So let's suppose we have these three equations. In these three equations, I want you to analyze and determine the point of intersection. So first off, you can see the normals are not collinear. You can just see that from inspection. So this gets rid of some possibilities. That means there's no planes that are parallel to each other. Okay, so we should check to see if they're collinear, or sorry, coplanar. So I'll check out the vector 1, 2, 1. I'm going to cross it with 1, -3, -1. And then I'm going to dot it with the vector 2, 1, -1. So I'm going to work out my calculations here. Okay, so -2 plus 3, 1 plus 1, and -3 minus 2. Got a dot with a vector 2, 1, -1. Okay, so that's 2. That's another 2 being added, and that's the value 5. So this does not equal 0. So normals are not coplanar. So that means that this actually intersects in a point. So let's find that point of intersection. And again, when it says determine the point of intersection, it not necessarily means there is a point of intersection. There could be multiple points of intersection, as in they form a line, or they may form a plane, or they may not even intersect at all. Okay, so what you do is you start by eliminating one variable from your first two equations. So I'm going to eliminate the variable z. just by simply adding these two equations. So I get a fourth equation I'm going to call number 4. I'm going to do the same thing, and now I'm going to eliminate the variable z from equations 1 and 3. Again, I could just simply add these. To eliminate. Now in this case, this plane actually generates something that I can actually divide a number of all by. So I'm going to divide all by 3 to get an equivalent plane, which I'm going to call number 5. Now remember that in grade 10 we saw that using elimination or substitution just actually changed the orientation of the plane or line in those cases and just found the same solutions. So you're still finding the same solutions here. So now based on this, you just use your new equations, so equation 4 and 5, and I'm going to eliminate the variable y. As you can see, they're not the same. If they were the same, then this means that you could possibly have a line of intersection. So here again, I'm just going to add these two equations. I get 3x equals 3. That means my x value is 1. So I can take that and I can substitute back into one of my equations here, either 4 or 5, to solve for y. That means my y value is 2. And I can substitute x equals 1 and y equals to 2 into one of my other equations, let's say equation 1, to solve for z. So we get a point of intersection of 1, 2, 3. So let's try that again with another problem. I encourage you guys to pause your video and try this one out on your own. Okay, so again, I'm going to label these 1, 2, and 3. You can see the normals are not collinear. Just by inspection. So now I'm going to check to see if they're coplanar. Because again, it does ask me to analyze, so I need to analyze them. If it does not ask you to analyze, you don't need to. You can just try to find their point of intersection if possible, or points of intersection. Again, you don't know if this is equal to 0, so do not state that it equals 0. You want to see if it works out to be equal to 0. Okay. So 8 plus 3, 6 minus 4, and negative 1 minus 4. Okay. So this does equal 0. So normals are coplanar. So to show you again, I'm going to scroll back a bit. Coplanar could be a triangular prism right here, or it could be a sheaf of planes. So we're just going to verify what type. See if there's any solution. So again, I'm going to eliminate some variable. In this case, I'd like to eliminate the variable x. I think it might be easier. So I'm going to take equation 1, I'm going to multiply by negative 2. And I'm going to add this to equation 2. Okay, so again, I'm going to do the same thing, but this time I'm going to eliminate the variable x from equations 1 and 3. So equation 1, I'm going to multiply by negative 3 this time. Make sure you're multiplying all the values by negative 3. Most common errors that you forget one of the numbers. And again, I'm going to add these two equations. So in this case, I get negative 20y minus 8z equals 19. Well, you may notice that the negative 5y minus 2z is actually 4 times bigger than negative 20y minus 8z. However, the negative 15 and the 19 are not multiples of each other. So when we do elimination here from equations 4 and 5, so if I take equation 4 and multiply by negative 4, I get 20y plus 8z equals 60. And for my fifth equation, if I just leave it as is, and you add these two equations, you'll get 0y plus 0z equals 79. This shows you have no solutions whatsoever. So it did not intersect in a line, and therefore it forms a triangular prism. If you want, you can state that triangular prism shape. If you want, you can even find the lines of intersection between just two of the planes and then find those equations, but it's not necessary, and you can state no solutions at this moment in time. And thus concludes this lesson.